Whoa. What's up? Welcome back. Today we're working on my image to ASCII neural network. So the idea is that we want to take picture on left and turn it into text on right. Now what we're seeing here is still a picture. However, if we zoom in and look closely, these are made up of like UTF-8 characters that have like been sampled from some font that we're looking at. And the idea is this labeling process, or sorry, this generation of this, we'll call it, is a little expensive. The idea is, hold on, that we don't want to just do something stupid like if we were to just pick the brightness of each character and compare it with the brightness of the scene. That doesn't look as good as if we try to do some form of like intelligent glyph matching, right? So like, the idea is that if we kind of like look at the image as we break it up into sections, right? So say we do like 1, 2, 3, 4, 5 sections on each dimension or each axis. And say you have like an X going through here. Boom, 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 boom. All of these guys are filled in. If you were to just pick like the glyph that has like the closest brightness in it, you might get something that looks like this, where this is filled in and the top isn't. But like almost certainly you should be picking like an X, right? Because that matches like the form of this best. And so we like experiment with some metrics. I don't think we're quite there yet. After flipping through some more samples, I don't think we're at like the best answer, but we have like an answer that basically says we're going to like blur the glyph a little bit, and then we're gonna like just compare it pixel by pixel with the initial image, and then weight that, like give that each character a score, weight that score a little bit by brightness of the glyph as a whole, and then pick the one with the lowest score. Great. And that turns out that it's like not trivially slow, right? Like to do like a 1080p image on the CPU with SIMD and like multiprocessing from Torch, that's giving us like maybe like a second and a half, 2 seconds. And the same, if we train like a really shitty neural network to predict the same thing, we found that at least on one image, we were getting pretty decent results within like in 0.01 seconds, so like 10 milliseconds-ish, which is what? That's like 200x speed up. And that brings us from the range of something where we couldn't do it on the CPU feasibly in real time to something that we could. And so it's kind of like the idea of the project is we're just kind of hoping to get to a point where we can get something like this kind of relatively quickly and experiment with neural network training along the way. And so where we got to last stream was we expanded our training data set from like a one sample image. So but previously we were only looking at this guy. Let's see if I can find him. We were only looking at basically this guy. One image of like a little mountain range. And we expand our training set to have more data in it that we pulled from some like training set. And we're not seeing like the neural network output here, we're just seeing like the manual labeling process. And what we found was the performance was like not nearly as good as we expected it to be. And so at the end of last stream, we said, well, what if we were to like try a bunch of network architectures? And we started and we were like, oh, it's slow to train still. We've done a lot of work to improve the performance, but like it's still not fast enough that we can find like quick results. And so then I was like, okay, I'll try off stream. I'll try a few things and I'll come back. I get off stream. I try a couple things that are not really, they don't have like the performance improvements I expect to see. And I think, well, maybe I'm just not training for long enough, or like maybe I need to like adjust learning rates and stuff like that. Maybe if we left it for a while, it would get okay. And I just didn't have the patience to do that. Right? I was thinking like, well, if I was to actually try to implement, if I was going to like actually go down that road, I would want my training to go a little faster. And so I was like, what if I started caching my samples? And I started writing that last night, or like I like typed like the first couple characters, and I was like, we should do that on stream. That's a good stream topic. So that's the goal for today, is we want to basically, instead of labeling all of our data on the fly, pick a bunch of images, pick a bunch of samples from those images, pre-label them, and then the label generation, which is like the slow part, will eventually, hopefully, be a little bit faster when we pull them from like a database of some form. And so I don't really know like what that's going to look like. I think that probably we want to start with picking like what data do we need to store? How are we going to store it? What's like an efficient way? Do we want to use like one JSON file, one big Sqlite database? Do we want to like leverage the file system in some way? Not really sure. So we're going to do something like benchmarking and testing there. Then once we've picked something, we're going to do some like implementation. And then if we get there and we're like in a good, we've done that like in like a decent number of time or decent amount of time, we'll probably start looking at actually training based off of those generated cached samples, whatever. I see that we have a raid. Thank you, MetaMe, for the raid. Appreciate it. If you guys are new here, we've been kind of just working on, right now, we're working on this like image to ASCII neural network project. So I just kind of went through a little bit of an explanation there, but there's a little bit of catch up in the top right if you want to catch up there, and we're just kind of getting started now. So basically we're trying to, we label data. Labeling data is slow. We're trying to speed that process up by pre-labeling a bunch of data and caching it. Maybe we're not going to actually train for the whole, like when we actually do our final version of this, we're not going to use that, but using it for iteration means that we can like cut down on the amount of data that we need to like keep track of, do things faster, get to answers faster. Bing, bang, boom. All right. So let's just get moving. Intro done. So I guess we need to think about like how many image, like what are we doing here, right? We have some amount of images. We've been kind of using this like validation set. Sorry, this training set here, ls train, which has a lot of images in it. And let's see, that's like around like 36,000 images. Okay, that's a fair amount. And like we're sampling these in our training right now. We're doing like, well, let's check actually. I think somewhere we write this down. We write down how big each sample is. So here we can look at our training output, and we're sampling 6 pixels by 9 pixels for each sample. And how big are these images? I guess we should just like open one and take a look, and we get like a ballpark. It's not going to be perfect, but we'll get a ballpark for like how much data we actually need to keep track of. Oh, fuck. We'll open this one. Okay, so this is like 680 by 512, 512 by 680. Sure. So we'll say like 700 by 500, approximately. So we have 700. Let's open up the calculator, or maybe Python. Python 3. So we have what, 700 by 500 pixels times how many images would we say? 35,000. It's here, 36,000. So that's about how many pixels there are in our training data set. And how big did we say our sample size was? Our sample size was 6 by 9. So approximately divide that by 6 by 9. Hand wavy, right? Like it's not going to line up perfectly, but you know, a little bit closer. And so that's what? This is how many pixels there are. So let's say that each pixel, or sorry, is this how many pixels there are? This is how many samples there are? Is that right? 700 by 500 pixels times 3,600 images divided by 6 by 9. So 6 by 9 is our sample size. So this is how many samples. So I don't even know. This is 1, 2, 3. Can we fucking... I wish that this was a number that had digits that weren't all the same so that I could actually fucking count them. But we can live the dream here. So we have 1, 2, 3, 4, 5, 6. So 200,000 approximately samples to keep track of if we were to pre-generate the whole training set. Now, how many, like, what are we storing for each of these guys? For each sample, we could take a couple approaches, right? We could store the actual sample itself. We could keep track of the label. But instead of keeping track of the actual sample, we could instead keep track of the like name of the file, as well as the x, y, width, height. But width height is going to be constant for all samples, so probably we can just get away with file name and xy, which is going to be, and maybe we could even get away with, instead of file name, if we sort the files, we get away with like file index, which is like what, 3. This is going to be an index, probably like an int 32, so 4 bytes, x and y. Probably can get away with like 16 or 2 bytes for each. So like, let's say 8 bytes times this much. So this times 8 divided by 1024 divided by 1024. So 1.7 gigs approximately of just, if we don't even store the samples, just the like index width and height. Oh, and the label. So that's actually going to be more. That's going to be times, let's say the label, let's say there's like 4 bytes for the label. So 2.6 gigs. 2.6 gigs. Okay, so the question is, how do we want to store that, right? You could, like, the simplest thing would be some form of JSON file, right? Python, just load JSON, bang, bang, boom, here's your labels. But can we, like, keep the label? Do we want to keep the labels in memory at 2.6 gigs? That's a lot. We could if it's on CPU, but if we're doing CPU training ever, then that, like, is pretty significant. My gut says that I wouldn't want to do that. So, like, pre-parsing the whole JSON file, I wouldn't want to do. And also, if it's 2.6 gigs, it's probably going to be pretty slow to process unless we do some sort of, like, intelligent pre-process, like, how do I say this? Try to use, like, a more optimized JSON parser than the one built into the Python library. I would bet that this would be slow otherwise. Another option would be trying to, like, put these all in the file system in some way, right? Then you can just, like, say, I'm going to ls this folder, and I'm going to pick one of the files in that folder and load it. But I suspect that that also wouldn't be very fast. I think metadata overhead per file would be more than is reasonable. So my gut says, without doing any, like, real hard benchmarking, but just from, like, running the numbers and thinking, my gut says, like, a SQLite database is a good fit for this, right? We have a lot of stuff. We want to be able to, like, sift through it quickly, filter it out, maybe, like, extract, like, batches of data at a time. Seems reasonable to me to throw it in an SQLite database. So I think that's what I'm going to do. And so what are we going to do? We're going to say SQLite database with some table in it. Probably only one table is good enough, right? We're just going to have, like, a table samples. And all he is going to have is he's going to have, or maybe two, you could, maybe 2 tables here. One, we're going to have, like, files, which are just going to have, like, basically a file ID and a path. Unless we want to just sort them, but it's kind of nice in case, like, our validation set ever changes. Maybe it'll be nice to, like, keep the mapping here. And then for samples, we'll just have file ID, X position, Y position, label ID. And so, like, maybe we should also keep, you could also keep the, like, character map in here. As in, like, label to character mapping. So here would that would just be, like, label ID car code. And that seems like probably reasonable because right now our character codes are generated by trying to render every single character that the font provides and discarding the ones that fail. So if we're not going to be re-rendering those characters, then there's, like, kind of no point. It's good to, like, just keep track of that here. Yeah, I think I'm reasonably okay with that. My gut says that will be fine and pretty quick to implement. So, yeah, let's do that. I could be wrong, by the way, about, like, if an SQLite database is the best fit for this. I wouldn't be shocked if we found that, like, I was wrong about the overhead of, like, 2.6 gigs of JSON, but hand wavy gut says SQLite. SQLite's fine. It's easy to work with. I assume. I actually haven't ever worked with it in Python, but I'm assuming. So, what are we doing? We're doing SQLite database generation. So at some point we're going to have to, like, create the SQLite database. Then we're probably going to have to fill the SQLite database, but I guess that comes from generate samples before training. Okay, yeah, sure. So let's just start with the database generation. I think Python 3 has an SQLite module built right into it. And looks pretty straightforward, actually. Okay. Looks straightforward from that. So let's start, I guess, in the context of like a test script. I guess we'll call it test Sqlite. And here, let's say that we are a Python file, so user bin env python3. That way, Linux will know how to run this. And then I guess we'll just import Sqlite 3. And let's kind of like just write down, we'll copy paste this stuff in here so that we remember what we want to do. Boom. And then we can close this guy. We don't care about him anymore. Okay. So let's just try like getting some data into a database in like about the format that we want. So let's say that we want like test.db. Connection is this guy. So this is a connection to the database. He doesn't like that I spelt Sqlite instead of Sqlite. What a whiner this guy is. You know, he's always telling me that I'm misspelling things. He's got to grow up. Just deal with it, man, you know? Just do what I think, not what I write. Okay. So we connect to this guy, and then we get a cursor, where a cursor... I don't really understand why I can't just act like... I can't just act on the connection by itself. I thought that you could, and like when I've used this other library, Sqlite. Hey, thanks for the prime, Rambert. In Rust, I've worked on with this guy, and I thought that this guy let me run with the connection directly. Connection. Yeah, I thought, well, maybe connection open. Maybe not. I don't see anything in here. He let me start transactions. And was there like an execute on here? There must be. Yeah, he did let me. So I don't really understand why this guy is telling me I need a cursor. But that's fine. We'll just pull it out. He's saying that you need it, so I should trust him. And okay, so then I need to like mix my tables. So we're gonna say cursor execute. Create table. What's the format? So here we're going to make like our samples table. And he's going to have a file ID, X, Y, label ID. Okay, easy. This may or may not be valid SQL. And I guess we're going to have to like put some data in there. So let's just like pre-generate some, I guess. I think I forgot a bracket here. There we go. So we can say what? Like, for I in range 50, right, we'll shove 50 things in there. We will say cursor, execute, insert into samples, values, and then there's probably some way to like inject the values from Python into Sqlite. Insert into this, values. This guy, they just put the strings in directly. Is there a way for me to say, like, I want to inject the values separately with, like, little placeholders? Isn't this, like, exactly what you're not supposed to do to avoid SQL injection? Not that I have to worry about SQL injection, but, you know. Oh, here we go. Values here. Execute many. He puts question marks here, and then he executes. Where does like the values get injected here? Oh, here he just passed them in here. Do I have to use execute many to do that, or does execute provide that like optional extra parameter? Okay, yeah, he does. He says parameters here. Okay, so we could do question mark, question mark, question mark, question mark, probably. I'm just kind of guessing, but we'll see. And then probably the parameters come in like this, and we say like, I, right? We're just gonna say every single one gets the same thing. Or maybe we're gonna do like I plus 1 plus 2 plus 3 plus 4. Just so that we can like see that the values that we're inserting are what we like expect. Okay. So let's run the script. No crashes. That's a good sign. Is our database there? Also a good sign. And I think there's like this browser thing that we can install. And let's kind of just take a peek. Take a little peek skis. And see if the data in there looks reasonable. No. Right, there's no data. That's bad. So probably we need to like commit our insertions. Where is their little thing? Insert into, yeah, you have to commit it. I see. Gotta write down that we want to actually, I guess like there, because for error handling, shit, I can't foreground my Vim job because it's like in the shell that I'm not in. God damn it. And it's like holding on to something, so we can just like kill. Who knows which one of these ones it is? Oh, god damn it. Okay, we'll just exit and foreground. And we'll say cursor.commit. No? Connection commit. That's weird. That's interesting. So all operations on this connection are like ephemeral unless I do this. That I expected to have to like opt into that behavior, but I guess that's fine. That's fine. No big deal. No big dealio. Okay, so we're gonna run again. Well, first let's get into the context where we have Sqlite browser so we can look at the results again. Give it a sec. Python 3, test Sqlite. He doesn't like that the table already exists, so eventually we'll have to deal with that, but for now, we won't. Actually, maybe we will never have to deal with that, because you could argue that if we're updating a cache, like we should be regenerating the values. You could argue that. I won't right now, but you could. And, okay. So in here now, do we have data? 1, 2, and we do have, like, what we inserted is what we expect, right? We expected to have incrementing on each row, and we see that we have, like, incrementing along the row as well, which is what we typed. So we understand how to put things in. Sick. And now let's just make sure that we understand how to get things out. Nope. We want to edit the script, not the database, obviously. So I guess somewhere we're going to have a way to select stuff. Sure. Okay, so we say cursor, execute, select everything from samples. And let's just kind of throw a filter in here for fun. So we'll say where file ID is greater than 25, right? Just make sure that we like understand this at all. I probably misspelled execute again. Execute. There we go. And then we call that a result. And we fetch all the answers. Cool. Cool. That makes sense. And then let's just see what we get here. So test Sqlite. We should probably just at the beginning of the script for now nuke the DB. So we're gonna say what OS unlink, is it? Remove. Remove seems fine. Test DB. I guess we, instead of writing to like a database on the file system, we can. Yeah, fine. That's fine. That doesn't really matter. Okay. So here we did get all files that have IDs greater than 25, which is good. We could also do something where like file ID %2 is equal to 0. I think it will probably work. I actually don't know, but it does. 0, 2, 4, 6, 8. Cool. Okay, so I think we understand, right? We have an array of tuples where the tuples are the values that we requested, right? If we, in here, we wanted to say don't select everything, but we want to select like file ID to label ID, we would lose all of the XYs. Oops. We have to put these not in brackets. There we go. See, we lose like the XY values, but that's okay. Okay, so easy. Easy. So now all we have to do is like, I guess, do we want to deal with the files or anything, writing down their paths and the character codes? We can deal with that later if we want to. So we'll skip that for now, and we'll just say samples are the only thing we care about. So now, let's say that we need to, like, in our file loading, which I guess comes from this, like, nested dir image loader thing, we get our images by just kind of saying, hey, find all JPEGs in this folder. And I guess we don't really have any guarantee that those are sorted. So let's just say for now that we'll sort them. Sort is not defined. How do you sort in Python? Is it dot sort? Oh, sorted. A dot sort. Okay, sure. It's crazy to me that self.images.len is not valid, but self.images sort is. That's crazy. I would expect like consistency there, but whatever. Not that it matters. I'm sure that I make worse decisions all the fucking time. It's just surprising. Okay. And so what we're going to do is we're going to load from this nested dir image loader. So I guess we're going to say from lib image sampler import this. Then we're going to make one of these guys. So what does he have? He needs a glyph cache. I guess because he is also responsible at this point in time for generating labels. So that's pretty reasonable. And can we construct him if we just don't pass one of those in right now? I think everything might be fine. I don't know. We'll see. Okay, so we're going to say that our image loader, image loader is this guy. And I guess we don't actually need this. This is all we really care about, right? So let's just do this. We just want our images, and we want them sorted. And the image dir for now, we're just going to hard code as pathlib, path. What are our options here? Probably we'll start with the validation folder, which is like a smaller data set, just so we can get the kinks ironed out before upgrading to the big bad boy version. Which means that we also need to import this guy for that to work. We're not using this anymore, so we just delete it. Okay, so now we are going to go like for image in images. What are we going to do? I guess we have to actually generate the labels. So actually using the image loader does make sense here. I should have just stuck with that because in order to inject the data into the database, we're going to have to do some work. So let's say we need to generate the glyph cache. And there's also the extra thing that comes out of there, but we won't worry about that for now. So from lib image text import generate glyph cache. Boom. We're going to generate the glyph cache. I think that there's no required inputs here. Yeah, we could specify that we want them on our GPU for massive speed gains, which is probably reasonable. Let's do that. And then we're gonna create our nested dir image loader from val, and the sample width we're doing 6, sample height. I think that we have to calculate that based off of the aspect ratio of the glyph cache. So I think we say like sample width is 6, and sample height is just going to be the sample width times the glyph cache, the like items in the glyph cache, i.e. every character we render into like a box the same size. So this guy is like a thing that is like number of glyphs, which we call C by convention here usually, by height by width. So if we want like a sample that is approximately the right aspect ratio, we can just take the glyph cache and take its shape 1, which is its height, divided by sample or the shape of the width. Yeah. So we take the width, multiply by height over width to get height. So here we can say sample height here, sample width here. And if we got this right, we should see that sample height is like around 9, I think. Like, you know, a little bit taller than it is wide for a character on screen. And I guess let's return here just to make sure. He doesn't like that I didn't close this bracket because he's a little whiner. He doesn't like that I returned outside function, so fine. We'll put this all in a function for you. That. Fine, we'll close our quotes properly. He always wants me to do the right thing, you know? So 6 and 9, that's reasonable, but 9.8 is a little high, so we're just gonna floor him. Which is probably wrong, but I think consistent with what we're doing everywhere else. And so we pass in the glyph cache and the glyph cache device here. Here we go. And I think that's good. So we can say image loader is this guy. And now we can say we're going to iterate over all the images in here. So we're going to say for image in image loader num images. We are going to have to do something with those guys. So for now, let's just print image loader images image, just to see that we are iterating over what we think we're iterating. And give it a sec here. Okay, so that seems reasonable. They look sorted like we expected, and they are, yeah, I think that's fine. That seems fine. Not worried about it. Okay, so what's next? What's next? We are going to have to get the sample for each of these guys. So here we have no way to like, well, what do? We like open the image. We say how big is our sample going to be? Or how many samples are there in this image, I guess. Then we basically extract them. I think we extract them as like a linear array of samples. So let's just double check this. So we can say image loader. We'll call this image ID or ID. We'll say image loader get samples for ID. And let's just see what comes out here. I think we get... let's just like see what comes out. Fuck it. Okay, so we get 2 arrays. Let's print their shapes. That's probably more relevant. It is 2, right? 1, 2. So that's probably the data and the labels. We can probably say data labels is equal to this. I don't know which way. I think labels was second, if I read that correctly. And so we can say print data.shape labels shape. Okay, sure. Yeah, so we got sequential, like one-dimensional array of samples of a fixed size, right? So what is maybe not super clear from this is how these are laid out. But for now, I just think I'm gonna like leverage the information that I know that like these are basically laid out this way. So they go this one, then this one, then this one, then this one, and this one. I think. I'm like 95% sure that's right. Because in our training script, or maybe our benchmarking script, we do extract the labels, and somewhere we like write out an image, rendered full image. So we extract the samples, and we do assume that they're y then x here. Yeah, we just iterate them and we assume, which is fine. Okay, sure. So we'll just say, for now, there's like a soft dependency, or I guess calling it a soft dependency is kind of wrong. There's a hard dependency on the fact that the labels come out in this like specific shape, and that's okay with me. Okay, so the x position, I guess, so we're gonna have to calculate which sample it is. So I guess we're going to have to know how many samples would be per row. Which is reasonable. Okay, we'll go back. Maybe we'll export these as a 2D grid of samples instead of a linear array of them, because maybe that makes more sense. Maybe, because then we don't have to guess on what it's doing internally to like actually chunk these guys up. So where's that code? Extract width height samples. So here we return NHW. So this is number of samples, height, and width. And instead, can we just not do that? Can we say like num y, num x samples? Here, don't reshape. This is probably already the right shape here. Probably. 56 by 170. That looks about right. 56 by 113. Multiply those together to get 6328. Probably. 56 by 113. 6328. Yeah, okay. So these are already in the right order, and we expect our images to be fatter than they are tall. So this first one is height, second one's width. That all lines up. So we just have to not do this. Just delete this line. We don't need it, okay? And then presumably everyone's going to break who calls this, but we'll just kind of deal with that fallout later. Okay, so now when we call our test script, we see something that we don't expect. It's not what I expected here. Probably, oh, let's see. We have shape is 85-1, 18 by 11. Something with that is fucked. Oh, I'm sorry. This is input something. So somebody's just probably assuming the wrong shape here. I see, I see. So when we generate the labels after we extract the samples, probably, where is it complaining? It's saying compute glyph diff scores for samples. Let's just go look at that. Compute glyph diff scores for samples. So samples for comparison, he is now N, Y, and X. And we'll adjust the documentation later. That's fine. Or maybe we won't and we'll forget, and then future me will be like, what the fuck are you doing? But here we'll just adjust this. So before we were explicitly pulling out the number of samples, and we'll just pull out N, Y, and X, which is 0, 1. This guy, he does like a resize on the lowest two dimensions, so that's all fine still. Here, we need this to be NY, NX, 1, height, width. There we go. And then at the end, do we pull them back out? These dimensions might be wrong now. We're doing like a sum over dimensions 2 and 3, which is supposed to be width, height, and I think this will probably be 3 and 4 now, because we were going from, I believe, if I remember correctly, yeah, here we have written down that the scores was number of samples by number of characters by height by width, and this is now going to be number of samples in Y by number of samples in X by characters by height by width, which means that these dimensions are incremented by 1, hopefully. And let's just kind of see that we get something that's like a reasonable shape out at the end there. We didn't make it that far. Oh, we did. We got 85 by 85 by 1525, which I'm actually not sure is reasonable. So let's look at NY and NX here. We do have 85 as our input, so that seems fine. Number of Y samples by number of X samples by number of characters, that seems to be working okay. And so now the other one that's bitching about is this guy, so we're saying NY is 0 and X is 1. These samples, we're summing over dimensions 2 and 3 now to keep the shape. Increment those by 1. And now we are reshaping to, what the fuck is this? Why do we do this? This should do nothing, I think. Let's just double check though. So before we crash, we were at 85, 85 by sums. That makes sense. Glyph sums is this guy. Oh, maybe for broadcasting? We were broadcasting the difference in brightnesses, so let's here print out sample sums dot shape and glyph sums shape, and just see what are we trying to subtract from each other. 85 by 85, 1, 1525, 1. I see. So this should be we need to like make sure that we're trying to do a subtraction of NY, NX brightness. We're trying to subtract for each one of these brightnesses. We're trying to subtract it from something for number of characters brightness. So we're gonna have to do something like, to make these guys line up, you need like NY, NX 1 brightness and 1, I think 1 1c brightness. Basically, anywhere where there's like a new dimension, you need to like put a 1 on the other one. So this would be sample sums is equal to sample sums reshape 1 or ny nx 1 1, and glyph sum should reshape 1 1 c 1, and then we should be able to do this at the end, reshape to ny nx c. I hope. Back streaming video over myself wasn't working, but stoked to see how easy it was to start someone else's machine learning project. Any ML project I've built in the past to help figure out over dependency. Glad to hear it. Yeah, the Nix dependent shell thing is pretty sick, and we're lucky that I tracked my dependencies well enough that like I might have been accidentally relying on like external packages, but it doesn't seem like that was the case, which is pretty sick. Pretty sick. Didn't like this. Did not like this. So. Why not? Oh, because we did... Am I missing something? What was our glyph sums shape again here? It's not working the way I expected. So here we had 1, 15, 25, 1. Oh. This should be glyph sums here. I mistyped. I was trying to resize the wrong variable. Okay, so that's working. And now we are getting labels that are wrong, though, here. So these should be 56 by... These should have, like, width and height, and we're accidentally collapsing them down, so that's a problem. So we just have to figure out now where that's happening. So probably we take this scoring function, and we just have to take the minimum of dimension 2 instead of dimension 1. No. Print scores shape. So our scores come out as like number of samples in Y, number of samples in X, and then number of characters. And we just basically need to convert this into, we want to take the minimum on this guy. So it should be minimum by dimension 2, I would think. Scores got min, dimension 2. What is this guy when he comes out? Print this. What is he? So he comes out with values and indices. And values, so say what? Values indices is equal to this. And values.shape and indices.shape. These should be the same, probably. But I don't know what they are. 85 by 85. Oh, no, okay. So that's right. Sample size, we have 85 height, 85 width, and we've broken those down into 85 by 85. So we should just be able to return the indices as our labels. And I guess it's possible that somebody else is assuming a bad width and height for these guys. Let's run the test script again. Oh, maybe that is right. Okay, so we're getting 85, 85, 85, 85. Yeah, okay. These are lining up. So now we're getting labels for each thing in each sample, height and width, as well as our data for each thing in height width. So I guess, do we actually care about the data here? I think no. I think we only care about the sample, or the labels. And we just insert those into the database. So we can say, insert into samples, values, bang, 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 where the file ID is going to be ID. The X value is going to be, I guess this is just, we're going to call it the sample. Okay, yeah. We're going to call it with sample. So we're going to say for Y in labels.shape 0, for X in range labels.shape 1, we do an insertion. So this is ID X, Y, label. Where this is labels YX. Sure. Yeah. Seems reasonable. So he doesn't like that that's a tensor, so we probably have to convert this into an integer for that to work okay. And otherwise, I think we can then just commit this at the end. And we'll skip this fetch all for now. I just want to get the data in, and then we can look at it with the Sqlite browser. So this is pretty slow, to be honest. It could be because of these, like, I wonder if we could get cheeky and avoid these loops by doing something like converting them into a list, like with torch stuff. It'd be interesting to know if most of the time being eaten up is by this or by this. So we can actually check that, right? We can say import time is the time taken up by generating the labels or by inserting to the database. So we can say label gen time is equal to 0. And we can say that the database insert time is equal to 0. And we can say start is equal to time monotonic. Database start is equal to time monotonic, and then we can just say label gen time, or now, I guess we'll say it at the end, is equal to time dot monotonic. And we can just say label gen time plus equals database start minus label or start, and the database insert time is increased by now minus database start. Easy. Easy. And then we can just say print label gen time, and then database time. This is database insert time. There we go. And let's just get a feel. So it looks like the label generation time is taking a long time, but the database time is taking even longer. So there probably is a way to optimize this. But maybe for now, we're just going to commit every one of these. And look at the data just to make sure it's like sane. Okay, so that's like a few. And let's just Sqlite browser. Fuck. Oh, I probably just deleted the file. Okay, we need to let it go again. Give it a second. Boom, 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 boom. Easy. And then we open it up with Sqlite browser. We look at the data. And we do see file ID does seem to be consistent. We see our X probably is wrapping faster. Cool. And the Y is still incrementing slowly. Our labels are not bullshit. And so it looks like we probably have a system that is working. And we just have to formalize this script a little bit. So let's say what? Like, I guess I'm trying to think, do I want to add in the work now to like validate that the file IDs are the same? We almost certainly should, right? Like skipping out on that seems, fuck it. I was gonna say it seems like prone to error, and it is. But I just don't care right now. We'll probably get bit by this later, but that's fine. Okay, so let's get some like argument parsing done in here. From argparse import argument parser. Yep. And what's our thing going to say? We're going to say our input is going to be the data dir, which is going to be, or I guess we'll say input. We'll just call it input. Fuck it. We'll call this input path. Output is output db path, or we'll just call it db path, I guess. Makes sense. Device being passed in also makes sense. And so now our main should take in an input path, DB path, and device. We do this bullshit like thing in Python where you can say parse args, and this will give us back like some sort of like dictionary-ish structure, but not quite. So we put it in we say vars to make it like a dictionary, and then you do this like double star shit to basically say like for each item in your dictionary, pass it in as like key. We have key value. This will call main with like key equals value, which is like just really fucking weird. But I don't know, it's like a thing Python does, and it makes my life easier in this case. A little bit of magic for what I would consider large gain here, where I don't have to like, otherwise I'd have to say like main args and then say like args input path. I don't know, I don't like that as much as like having it defined here. Feels like a little bit more type checked or whatever. So here we pass in device equals device in both these places. I think otherwise everything's fine. We don't hardcode val here anymore. We take in the input path. We should probably take in the sample size here as well. As an integer. So here, I think we don't need a custom destination, but we do want to say dtype is equal to int. And here we take in the sample width. Instead of hard-coding testdb, we use the db path. And everything else might just come for free here. Let's see. Sure. There's probably like some consistency checks that we're gonna have to get in later as well. Like if we type the wrong sample width here and we're sampling at like 10 pixels, but we train at like 6 pixels, and that's kind of fucking weird. But that's fine for now. I just want to get like, we just want to get something, and then we can iterate and improve as we get frustrated. I find that, at least for myself, the only like the biggest motivator for fixing any problem is just anger. Every time it's anger. So we can see where I get pissed off when there are bugs, and then we'll fix it then. Okay, and then otherwise, is this like good to go? Might be. And then, so let's move this from test Sqlite into something a little more official. We'll call it generate dataset cache.py. That sounds professional, doesn't it? And I guess we'll maybe run our linter, because it's gonna, there's a lot of things that are broken right now, so we'll only handle this one for now, because I'm in this like kind of work in progress state, so there's a lot of things that aren't passing lints right now, so we'll deal with that. Again, offload work to the future me who can't hit me back. I just keep hitting him and he keeps saying stop it. Okay, I guess you could argue that this commit can go at the end, but whatever, this is fine. Yeah, I don't see anything in here that looks like it needs to be fixed up. Oh fuck, I'm editing the wrong script, god damn it. Move test Sqlite to generate dataset cache. Git add generate dataset cache. Git commit whip generate dataset cache. And we'll clean that up later. All right. So we could kind of argue that like the database has been generated. We don't really know if it's any good, but we do know it's generated. And let's generate like a few samples, I guess, and then figure out how to get them loaded. So we'll say that we're working on loading, even though we do have like a few seconds of work to do to like get a bit of cache working. So let's run that script. So maybe we have to chmod plus x generate dataset cache. We probably have done that yet. Generate dataset cache. Oops. We brought the little exclamation mark here, which is very important. Now we can run this a little bit, but it doesn't like something here. Parse args. These are all required. I don't understand why something's not working here. Oh, because dtype is the wrong word. It's type here. Generate dataset cache. Boom. Okay. So input val, output val.db, sample width. We've been using 6. And device CUDA. And we just let that run for a little bit. Just enough so that we have samples to load, so that's probably good enough. Boom. And now we need to do the stuff to load it. So what does that look like? First, let's make sure that we commit those changes. Oh, there's actually a lot of changes that we didn't commit here. We should probably commit them all. And maybe we just fold them into the other one. Fuck it. We know these are all related to the same shit. And I'll clean things up later. And now we need to do loading. So what? In our image sampler, let's say that our nested dir image loader, he has an optional input that is like cached data path, which is like a union of none or path or stir, maybe path like. I think that's the word for this. So we can say from typing import path union and path like import path like. He doesn't like it here. It's from os import path like maybe. Boom. Okay. So now we can say that our cache data path, if we get this, so if we get this, we're going to take like a different path. Do we think that these are similar enough that they should live in the same world? No. I think no. These should probably be completely separate classes. Because this glyph cache is like where we use the glyph cache to like generate the labels and stuff. We don't really need that here, so it doesn't seem reasonable to say that we're going to like switch on behavior. These like get sample things are going to look totally different, so I'm just going to actually make a new class. Class nested dir cached nested dir cached labels loader. That's a sentence. We're gonna take in the same thing here, but instead of the glyph cache, we're gonna take in the cache path, which is now guaranteed to be a path like. We're gonna say self.cache path is equal to path. Cache path, great. Easy. What else do we have in here? We're gonna have to load the images the same way, so we're gonna have to say, we're gonna make a function here called get image list for image dir, because we want like to make sure that these guys stay consistent with each other. So nothing too crazy here. We're just gonna go boom, copy, return images. Easy, so self.images is equal to get image list image dir for both of these guys. Bang, bang, boom. We're gonna copy paste the sample width stuff. Those also, we want to pull those in. And I guess we don't want to save like the cache path as our state here, but maybe like the Sqlite connection. So we can say what? Self.connection is equal to Sqlite. We need to pull that in. So import Sqlite 3. Open Sqlite 3. Connect to cache path. Sure. Sure. And this is going to look the same. No image is going to look the same. Get sample is going to look probably similar in some ways and not others. So let's say that we have another function that actually turns the image into its sample. So def image path to data to samples. Maybe? Sure. So this will take in a image path, which is a path like, and he's going to return a torch tensor. And the torch tensor is going to be, where does this colon go? Here? Here. Yeah, sure. Okay, and so here he's going to output returns image as it returns image broken up into samples of n, y, and x height width. Yeah. Where ny is number of samples in y dimension, x and x is number of samples in x dimension, h is height of a sample, w is width of a sample. Okay, which means that we probably need to take in the sample width and sample height here. This. All right. And then we do this. Oh, and this isn't actually how this guy works. But that's okay. So, but we're trying to reuse code here, so this is actually kind of important that this matches. So instead we're just gonna say return image. So we're gonna get, instead of getting this and extracting the samples, we're gonna say image path to NumPy. What do they expect here? They expect I open him, I convert him to black and white, then I resize him. So I think I just want to say we'll just call it open image. And this is not going to return this anymore. This is going to turn a PIL image, or just image probably. Oh, except the fucking typing on this is broken, so we'll just say we'll just won't annotate the return type, and we'll delete this. Okay, fine. That works for me. We'll call this a str. That's fine. Like this. Okay. So here we're gonna replace this with open image here. Self images I, and that's gonna look very suspiciously like the thing we're doing in our cache thing. We don't have to worry about breaking up the number of samples because we, in our database, store where each sample is. So we can say labels, or yeah, labels is going to be self connection cursor. We need to get a cursor to this guy, so I guess we'll call him cursor. We're say cursor execute select. You could put star here. Maybe that's like arguably a little dangerous. But I guess we can just assert on length later. Or fine. We'll call it file ID XY label. But we don't need the file ID. So we only need XY label from I already forgot what we called it. From samples where file ID, is it single equals or double equals in Sqlite? Sqlite where? Where? Where file ID is equal to, and do I pass in question mark here? And then we say I, like this. I actually don't know if this is reasonable, but we'll find out pretty quick when we try to run it and it doesn't fucking work. Okay, so now we need to turn these labels into something. So how do we did this somewhere already, but I forget. I already forgot. So there's a select here, and this just comes out as rows. And I think we call it fetch all. Yeah. There we go. So here we're gonna say rows equal this, and we'll assert, or maybe we can do for row in. Maybe that's fine. And we're gonna say assert row length is 3. I don't see why that would be wrong, but we should just double check. And maybe we just print the row actually while we're here. And maybe we'll just call this our thing. So we're gonna go into our test script again, and we're gonna do something completely different than this. We're gonna say from lib image sampler import Nested dir cached labels loader. Jesus, what a name. So we'll call it loader is equal to nested dir cached labels loader. And we're going to come this comes from val, as well as the sample width we know was 6, the sample height was 9, and the cache path was something. Val.db probably. Python 3 test.py. Does that crash anyway? No, looks like we're fine. And then we're gonna say loader get sample 0. And we'll just see what fucking happens. No such column label. Label ID? Maybe is what we called it. Yep, okay. So here we have our samples and our label ID. And so we should be able to now extract samples from each of these guys. So we're going to say data is equal to a list of something. Labels is equal to a list of something. And we know that we are expecting to this should be ny, nx, height, width. And this should be ny, nx, label. Okay, so the data for this sample is going to be, well, we're going to have like some start and end x. So the start x is going to be the row 0. Oh, fuck. Okay, we should name these. X is equal to row 0. Y is equal to row 1. Fuck. X, Y, label is equal to row. There we go. Nice little tuple destructuring. List destructuring? I don't know what it's called in Python. Or any language. I'm just making shit up, but I think I've heard the words destructuring. The image start x is going to be the sample x, which sample along the x-axis, times the sample width, which is a self parameter. The end x is going to be the image start x plus the self sample width. We're going to do the same thing for y. So this is start y, but with height. Y here, Y here. Okay, and then we're going to say image. We're going to say that the data for this guy is extracted from the image. So data is equal to image. We'll call it sample data. We have to make sure that we're not clobbering a name there. So this is going to be image from the image start Y to image and Y. And image start X to image and X. Okay. Okay. And then we're going to say data is actually going to be a 2D array here for now. And we're going to say, Jesus, what are we going to do here? I guess we need to make sure that we have enough rows in this for our given Y. So we're going to say while data length, this is ugly, is less than Y, data.push append a new list. So we're kind of like slowly constructing a 2D array, like a list of lists here that represents a 2D array of samples. Then we should be able to say data Y. Fuck, we actually don't know if our X is in the right position here either, which is fucking annoying. So here we're gonna say row data is equal to data Y, and we're gonna have to do the same fucking shit. Where we say while len row data is less than X, data.append none, I guess, which is fucking annoying. Row data.append none. And this actually has to be +1 for each of these because, or less than or equal to, I guess. There we go. And now we can be able to say row data at X is equal to the sample data. Okay, and then at the end of this, we should be able to print data, and we should see a bunch of tensors. I guess, but we should see a bunch of tensors, and none of them should be none. We should see a 2D grid. Image is not fucking subscriptable. Okay, so we go to image is open image, and this needs to be turned into a numpy array torch tensor. Okay. Let's see it. Okay. That's hard to look at. So can we actually convert this into a torch tensor just automatically? I actually don't know if that will let us, but we can see. Print this. Certainly that'll crash, but we can cross fingers. Only integer tensor of a single element can be converted to an index. Yeah, okay. Okay, so for each, what we should have is we should have a list. Our thing should look like this. It's a list, and each of these rows, we have a list of tensor. There's a torch.cat, which basically turns these tensors into like another dimension. So we can say for row in data, you can say that tensor datas is equal to this. And we can say tensor datas append torch cat row. And then we should be able to say tensor datas is equal to torch.cat tensor datas. And I think that should give us something that has like tensor datas shape. Hopefully that gives us something. I actually don't really know, but we'll see. Tensor is not defined because I left this like fucking scratch note in there. Okay, not quite right. Not quite right. So let's actually look at the sample that we're inserting for each time. So let's see, print sample data shape. So these are 9x6, so that's correct. And can we maybe look at print row here? Is the stuff in each row that we're trying to get, are these reasonable? Maybe we put row 0 shape or something. Okay, so this is all reasonable as well. Each row has like tensors of the same size. So this torch cat is probably shit. Not shit, but like I'm calling it with the wrong arguments. And it's the dimension that you're catting over. So probably want like dim equals. Do you have to like specify a dimension there? No. Dim 0? No, that's not what I want. So I have 9x6, and I want to like stack these or cat them along like a new dimension. So here you take the thing. Here they're doing XXX, and their X is a 2 thing, and they're concatenating it, but it's not along a new dimension. I see. So these are just like kind of like getting stuck next to each other. Is it torch stack that I'm looking for? Concatenates along a new dimension. Yeah. There we go. So we now have 7225 by 9x6, and we just do the same thing here with another stack here. 85 by 85 by 9x6. Solid work. Very, very sick. Seems reasonable. So there's some like absolute bullshit happening here. We're going to have to adjust some of the, we're gonna have to split out some functions here. So we're gonna say this stuff where we say, make sure that the thing is long enough for my index. We're gonna say def ensure valid insert for a list L and an item that is untyped. We are going to we'll call this item. We'll leave the list as single variable because I can't type list because that's like a function, so we're just gonna say L there, fuck it. And we'll just do this. So and we should also here have a placeholder that we have to insert. Placeholder. So while L, the length of L is less than Y, not Y, item. Nope, we need an index here as well. Well, this is less than index. We append the placeholder. And then, once we get there, what do we do? We insert that thing. L index equals item. Okay. So then we can say ensure valid insert, which doesn't look like what we wrote here, by the way, but that's okay. So you have data, placeholder, index, and the item, which I guess we don't know that we're trying to insert here. I guess we don't need to insert the item here. We just need to make sure that the placeholders have been set. Yeah. And then we can say we extract the row data. Nice. And then we say ensure valid insert for row data with placeholder of none of X. Okay, there, that seems reasonable. And we just do the same thing for the label. So here we say label. We still insert brackets. Still the same length. Row data is the label. Row labels is equal to this. And we do the same thing here, where we ensure valid for row labels, but this time we put none in here for X. And the row labels X is equal to label. All right. Sure. That's kind of ugly, but it works well enough, probably. We run the script, and it probably should still, boom. Int has no len. Fuck. While len L. Am I high? Am I high? While len L is index, how is that an int? When we pass in, oh, because I'm fucking high. This should be labels, not label. Int object is not subscriptable, because this is again labels, not label. Okay, we're back, and now we just say what? We need to do this like torch concatenate as well. So we'll probably pull all this out and say def 2D or tensor list 2D to tensor. Sure. So we have L is our list, and we're going to return a torch tensor, and we're just going to basically do this. And I guess we call it data instead of L. Little nicer variable name. Return tensor datas. And so here we should be able to say data is equal to tensor list 2D to tensor data, and label is equal to tensor list 2D to tensor label, plural. Then we should be able to return data and labels. And we should be able to then run our test script and kind of see what happens. So he doesn't like this because they're ints and not tensors. So I guess here when we insert the label, we should be doing a torch tensor of the label so that it has like the expected data type. And we know that these are going to be torch int64s because they're supposed to be indexes into a tensor, which torch wants is int64, which is reasonable. And now we can go back into our test script and kind of see what we get. All right, seems probably reasonable. We're gonna have to. What probably makes sense is trying to render out both the samples reconstructed as an image and the labels reconstructed, because that will guarantee us that we get we have something sane. So we can say for y in labels dot shape 0. For x in labels shape 1, we can print labels yx, and convert this into an integer, and then convert that into a character with end equal to nothing, so that we don't new line. Here we print an empty new line. And these should be ranges. And hopefully, if we do this, we should see a reasonable ASCII art printed on screen. Hand wavy. Well, that's not good. They don't even line up. Which is fucked because it's a monospace font. Am I high? Print Y, print labels, labels shape. Let's just double check this. So our labels shape should be 85 by 85. So this is concerning. It's possible that we're not properly filtering out characters with 0 width. So there might be a problem there. So it might be actually worthwhile to actually do our, I think there's like, I have a text renderer somewhere. Image to text. We do have this like text renderer from the glyph cache. We can say glyph cache is equal to generate glyph cache. And we're just going to hope to God that the labels match up here, which is a stupid thing to do, but we'll have to figure that out later. And then we have like a text renderer, which takes in the glyph cache. And let's just see if we just happen to try to render these labels. Renderer, render labels, and we're going to reshape these into -1. I guess we're going to reshape this into labels shape 0 times labels shape 1, which I guess is a squeeze, I think it's called, which is like basically just remove a dimension from this, please. Returns a tensor with all specified dimensions of input of size 1 removed. No, that's not what I want. Not what I want. All right, well, fuck it. We'll just do this. That's fine. And the number of characters per row is labels shape 1. Okay. And where is this going to go? This is going to return a output image that is in torch tensor. So we'll say image is this, and then we'll say image is equal to image.cpu numpy. Great. And then what? We write that image save, or image from array, image save, test.png. And we say from pill import image. Great. Now let's run the script. It's going to fail because I always fuck something up. Glyph cache is not defined, because this needs to be like this, probably. Probably I misspelled glyph somewhere. Glyph instead of glyph, as always. I will never misspell that, or I will never spell it correctly. And let's see if that test PNG looks... Okay. So there's... Okay. So there's a problem with, like, printing it, but we can at least, like, be semi... confident that the labels that we're pulling out of the database are like in the order that we expect. And so now we should just be able to do the same thing with the samples. So we can say for y in range data shape 0, or x in range data shape 1. The data should reconstruct the original image. So we're going to say that we're going to have like an output image is equal to torch tensor, torch zeros, import torch. That's important here. So we're going to say like zeros. I think that we're supposed to return these the data in like a range of 0 to 1 right now. I think that that's like what our network expects. Yeah, we do this like divide by 255, which we're not doing up here. So we should, in fact, do data over 255.0 over here. And so we're going to have our zeros are going to be, what? They're going to be the width of the sample times the number of samples. So we're going to say data shape 1 times data shape 3. D type is equal to torch float 32. And then we need another dimension for y. So this is data.shape 0 times data.shape 2. Ooh, maybe, I think. We'll see. Okay. So then we're going to, for each sample, inject that into the spot in the image that makes sense for that sample. So we're going to say, do the same like start x, start y thing, which I think just ends up being the same code that we did here. We'll check this in a second. So y is the y value of the sample times the sample height. That makes sense. All of this makes sense. We don't actually have our sample width and sample height here, which is interesting. Because the sample width and sample height... Oh, we have them just hard-coded as 6 and 9. Okay. Sure. Then we say that the image now is equal to the sample, which is data yx. And then we should just be able to like take that image that we collect all the samples, put them back together, and if we write that guy out now, image from array image.cpu.numpy, we have to be careful here because these guys are normalized. So if you multiply by 255.0 and then convert these to a uint data array, because that's what the image library expects. So we do this, CPU, numpy, save, test.png, or test image png, we'll call it. So hopefully that runs okay, which it seems to. And so now we have this guy and this guy. So this is the reconstructed input. Nope, not this one, sorry. This one is. Which does, in fact, look like a proper image. There's not like weird stitching issues or anything. And the left one that is like regenerated from ASCII characters is like reasonable as well. So it like kind of matches what we see in the reconstructed image. So it looks like that's actually working. Hand wavy, right? We don't have like major confidence, but we have some confidence. So we can say that this was, instead of actually loading samples during training, we can say, what have we done up to this point? We have reloaded samples from database. And now what I kind of want to do is I want to like see like, was this worth it? How fucking long does this take? So let's just say at 1:27:35, we are going to do some benchmarking of loading samples from DB. So how long does this take? Hand wavy, let's just say start is equal to time monotonic, end is equal to time monotonic. We need to import time. And we'll say print loading labels from database took this many seconds. Point 1. Fuck, is that still feels really fucking slow. What the fuck? Who's taking all that time? Could be this. The like iteration of the retrieved data for Sqlite. Could be the like concatenation of tensors in some way. Could be this. Okay, so maybe we just kind of like log time for each section. Okay, so we have the opening image. I guess it would be nice to be able to like log this a little easier. What's the fastest way? We can say with timer and then just indent. Yeah. Let's do that. Just because I'm fucking tired of doing this start end shit. So how do you make context managers here? Python context manager. This is going to end up taking longer than if I did it by hand, but I'll be less angry. And that has some value, probably. Okay, so you have a context manager, and you can create just as a function that yields a thing and a release. Okay, yeah, easy. That's easy. I'm down for that. That actually won't take that long at all. Not long at all. So we can say, where did I type that with timer shit? Is that gone? I think this is the first time I've ever seen you get annoyed enough over something to fix it. This one, the start and end labeling, it pisses me off so much, man. Okay, so we can say we have a context manager, and we can say log time, we'll call it, and he's gonna take in the like name of the thing. So he's gonna call this like tag, I guess. And we're going to say try yield something and finally something. So at the end, we are going to log the time. So we say tag is end minus start. End is equal to time monotonic. Start is equal to time monotonic. And here, I guess we do start is equal to time monotonic here. So it's guaranteed. And I think that actually will probably do what I expect, oddly. So we can say with log time open. I'm just curious, like, does that do what I want? Sometimes it's easy, man. So opening the image is taking 5 milliseconds, which is not that long. With log time Sqlite iterate, we do this with log time tensor conversion. Do this. That's so sick. Okay, so the majority's in like Sqlite iteration, but let's for now say that we don't do anything in the Sqlite iteration. We just do the iteration and we just see, right? Just iterating rows and doing nothing but looking at them. Still is taking basically no time. Oh no, that's still 10 milliseconds. And our total time was 100 milliseconds. Wait. Loading labels to different databases took 0.1 seconds, but the addition of all of these subcomponents is only to... Oh yeah, it's the Sqlite iterate is taking like it's taking like 85 milliseconds, which is like fucking long. Okay, so, and when we turn this off, the Sqlite iteration is still taking that long. No, it went from 85 down to 10. 85 milliseconds down to 10 milliseconds is like pretty reasonable. Or not, maybe not as reasonable as I would like, but not awful. So let's try doing like a fetch all here. Would be nice if there was a general purpose system profiler. I think there probably is, and I'm just not using it. So we're gonna say rows equal to this guy fetch all instead of iterating them all one by one. And so here, then we can call this, we're going to call this sample extraction. And we're going to say for row in rows, do all this shit again. Okay, Sqlite iterate takes, 11 milliseconds. Sample extraction taking 72 milliseconds. So... what is taking so long in here? Let's think. This stuff is probably pretty cheap. Almost all of this is certainly very cheap. This I could see being expensive. The like checking of the like 2D lists are like in the right state. I could see that being expensive in some way. We're gonna have to make a cumulative log time. Which I don't really know how I want this to work. So we want like an accumulator here. So instead of logging in time, we're gonna say like count time or something, because I don't have a good name for it. We don't have like a tag here, we just have the accumulator, and we'll just do the same thing here that we did before, but instead of logging, we say that the accumulator plus equals n minus start. And I don't know if I don't know what this does actually. If this adds to the, I don't know if like if this thing's like an integer that comes in. I think of everything in Python as like pass by pointer, so I don't know if this is reassigning the label or actually assigning the data. Time to search up a Python profiler. Well, I mean, okay, so the reason I'm doing it this way is because I was using CPython the other day, or cprofile or something. And I was kind of annoyed that like it seems like it's like sample based. And it didn't feel correct. Like when I looked at the results of like what it logged, it didn't seem like it matched like my intuition and my like manual timers. And I trust the manual timers a lot more because like I think the way that these profilers often work is they like interrupt your program every once in a while. They go like, I'm gonna stop now, I'm gonna stop now, I'm gonna stop now. And then what they do is they're just like, okay, I stopped. Where the fuck am I? Right? And if it's not doing that fast enough, then you won't get accurate enough results. Hand wavy. And so this I trust more. Okay. So I think if I just say class time, and in here I say init self. I say self dot accumulator is equal to 0. If I then pass in the accumulator here and I say timer accumulator equals end press start, I'm like confident that this will edit the outside thing. And like, dude, the way like Python's like simple in a lot of ways, but I don't know how the fuck like as a new programmer you're supposed to understand like the fact that this modifies external scope, but this does not. Like, I don't know how the fuck you're supposed to wrap your head around that if you haven't worked with, like, C and pointers. Like, they try to, like, hide the concept, but if you don't get pointers, I don't get how you can get this. I just don't get it. True, but you can mitigate by sampling a higher frequency or by running the operation many times. Yeah, but I can also mitigate it by doing this, which is more fun for me right now. So we can create a timer. And we'll say that this is, the first timer is going to be, we want to check like insertion versus, we want to check like the tensor labeling stuff, the list insertion stuff, and maybe like the sampling stuff. So we're going to have 3. We're going to have like sampling is equal to new timer. And we're going to call it, or sampling timer, list timer, and tensor timer. And so here we should be able to say like with count time with the sampling timer, with count time of the list timer, and with count time of the tensor timer. Easy peasy. What doesn't like here? Expected indented block, sure. I accidentally did this, which I shouldn't have. And then here at the end we can just say print sampling time took sampling timer accumulator, and we say list tensor. And this is sampling timer. Oopsies, I didn't have to replace that one. List timer, tensor timer. And I don't actually know if these are going to count anything, but we'll find out. Timer's not defined. Do you mean time? Yep, so we'll just write timer because I don't really give a shit. List time, low. Tensor time, medium. Sampling time, medium. That's interesting. That's pretty interesting. So that's actually not at all what I expected. So this is taking a while. I actually am curious if it's just the like row deconstruction or the Python thing. So sampling time 0.1. Yeah, okay. So it is like probably this actual extraction from the image is probably taking a long time. If we take that out of the timer, is the time low? Sampling time 0.002 versus sampling time 0.4. Yeah, okay. So this is expensive and this is expensive, which is surprising to me. Very surprising to me. Shit. Shit. So let's just hand wavy, see what happens if I run this on the GPU, just out of curiosity. Because the actual expensive parts are pretty, they're not where I would have expected. So this tensor has to be on device self.device for this to work. We need to log the device. So self.device is equal to device. I fucked up the bracket, so this goes like this. This will still happen on GPU. This now has to happen on the correct device. This. And we can see now if I pass in my test script device equals CUDA. Does this get like any faster? That's actually like significantly longer, which is pretty fucking sick. Pretty sick. Oh, but the open call there took way too long because it wasn't cached. Am I high? 200 milliseconds for opening the file? That's crazy. Oh, because it needs to copy to the GPU now, which is just making it take even fucking longer. Interesting. Interesting. Okay, so what happens... let's double check here. What happens if we compare this to the non-cached version? So this is nested dir image loader, and he is val69 with our glyph clash. The time to beat was what? 0.5 on GPU and 0.15 on CPU? We need to device equals device here. Oops, where device is equal to CUDA here. Fuck! Oh, wait, no. Loading. Oh, yeah, this is loading samples. It says loading samples from database, but this is now using the, like, other version. So it looks like we actually gained 0 fucking speed up here. That's super sick. Super fucking sick. Nested dir cache samples loader. Where this is val db. Forgot a comma? Fine. I did forget a comma. You're right. It's actually taking longer to load it from the cache. That's really unfortunate. And it is just like these sample extraction. I don't understand why this sample extraction is taking longer here than it would. Oh, it's because we're iterating in Python and extracting in Python, where when we do it with like the direct way, the sample extraction when we go from images to samples is like this like very cheap Python thing, or it's all in Torchland. Hui. Okay. So theoretically, we might actually be able to do this more efficiently. You could extract all of the X and Y positions from the Sqlite database at once, convert those into samples, I don't know how you get them back into the like 2D format, but maybe doable. I have to go to the washroom, so I'm gonna think about that for like 2 minutes as I disappear. Give me a second. Yo. Okay, I think this is doable. I think we can speed this up significantly. So here's what I'm thinking. Instead of extracting XY label ID like this, or maybe that's fine. We might be able to do something like clever, like say rows, everything up to position 2. This is going to be a bunch of XY samples like this. So let's actually reverse the order here so that they're YX, so that they match up with what Torch expects a little more. And we should be able to do some sort of like clever, actually it doesn't matter. We should be able to do something clever like when we do extract width height samples, we do this thing where we say, okay, we have these like numbers of samples that we're trying to get, and we get some like indexes for those samples, and then we like directly pull all of them out at once. And I bet you there's something you could do here, right? You could probably do something like Torch tensor this should give me a thing of like samples by 1 by 1 is kind of what I want here. Which would give me, for each of these, you have, for each sample, you have the Y position and the X position. Okay, let's just see if that, like, gives me anything. So XYs, or XYs equal this, and this should be X by Y, actually. I don't know if that will crash. It might. Okay, and can we do XY's shape? So this will probably give me, like, N by 2, probably, is what I'm expecting. Fuck. Not what I'm expecting. Oh, because this should be, fuck. Like this? Maybe? Maybe? Let's see. 2 by 3. Why is that such a weird size? Print rows. Oh, is this one of those, another one of those things where I have to do like index things? Argument of tuple slice list. What is my rows? Actually. What is this thing? Rows is a list of 4 tuple, or 3 element tuples. So this is A, B, C. And I'm trying to turn this into... I'm trying to turn this into N2. Number of samples by 2 elements. Right, so I need to get all rows. Let's not deal with this label ID shit. So these are now AB, which should be easily convertible. If I just do this, I should get something that's a lot by 2, which I do. 7225 by 2. That's exactly what I want. So this gives me 7,225 X, Y positions. And I should be able to convert those into what I want. So we can say, this is how many samples there are. Each sample is going to be of size sample width by sample height. And what do I do in this like extract width height samples? I create indexes into the original image. So that seems reasonable. So here I say my num y samples is going to be xy's dot max along the first dimension. Maybe along the 0th dimension? I think. Let's see. So if I say these are the values that I get, I need to print that. Print num y samples. I think. So this is 84, 84. Okay, that makes sense. Okay, so this is the number of samples X, number of samples Y, is this converted into a list? Which I think you can do. I'm not really sure. CPU, numpy or something, list, or I don't really. There's like a to list, I think. To list, maybe? And we can say print num samples X and num samples Y. That should give me 85 and 85. Or 84 and 84. Because that's the index, not the sample number. So this should actually be +1. Yeah. Okay, so now I have the number of samples, and we can create... Is that even relevant? I thought it was for a second, but now I'm not convinced. Because I need to figure out the width of each sample, but I already have that. So maybe this wasn't important, but we'll keep it around just in case. But we do need the width, so we have that, self sample width. And so what? For each X, we're going to create a bunch of indexes of the size sample width. And for each Y, we have to do the same. So torch... That's going to be similar to this. Y indices is torch arrange for the number of samples by the sample width. Then I reshape them in some way. Does that match up here? Let's just think about one dimension instead of two. X's is equal to XY's, all of them, but the first thing. And now for each of these, I want to turn these into a bunch of indexes that correspond to them. So we're going to say X's is going to be... I'm trying to go from basically from 0 to 0, 1, 2, 3, 4, 5 for each of these. So I guess you could do X's dot repeat. Can you do an you can duplicate it and then add for each one, but that doesn't really seem to make sense to me. You could do torch.arrange sample width. Yeah. So this will give us 0 to 5 essentially. And then this isn't defined self in this language. D type is equal to torch in 64. We can add this to the X's. So this here, we want this to be of shape 1 sample width. and we want it to be added to something of n1, which will give us something of n sample width. Oh yeah, baby, we're close. We're close. We're so close. We are close. So this, we need to reshape to 1, -1. So basically say just like, add a dimension, please. Or I guess you can say unsqueeze 0 plus x's, which we need to reshape or unsqueeze in the first dimension. And we should be able to say that the x indices is equal to this. Yes. And we should be able to print x indices shape. Come on, baby, give it to me. So here we have x indices shape is 2, 6. Fuck. Because I forgot to do this. I fucked up my indexing there. X indices shape is 7225 by 6. That's exactly what I want. And if we print them, yes, they should be reasonable. So these should be 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. Mwah. Okay, so these are the x indexes of each sample, and now we just have to do the same thing for y's. Y indices is self.sample height this time. Same device, same unsqueeze, but now we do y's.unsqueeze, where y's is this. Yes. And then we have print y indices.shape and x indices.shape. And I think that probably if these line up correctly, these are both 7225 by 9, 7225 by 6. I think that we can just do... What happens if we just look at the image now? Image, y indices, x indices? There's no way, right? Does that work? No, it does not work. Indexing tensors cannot be broadcast together with shapes. Okay, that's more what we were expecting to see. Okay, so these need to be broadcastable. Torch indexing. What am I missing? I just want those x's and those y's together. Oh, so I guess we stack, we concatenate them, or not concatenate them. We h stack maybe. We want to like go from basically we have the y and x indexes are n width, and we have the y indexes are n height, where n is the number of samples, and we want like n. What do we want here? Height width? Is that true? Yeah. Yeah, okay. So then we just need to, I think there's like a torch h stack. Stack tensors in sequence horizontally column-wise. So here you have 1, 2, 3, 4, 5, 6, and they stack them to 1, 2, 3, 4, 5, 6, and they go 1, 2, 3, 4, 5, 6, or 1, 4, 2, 5, 3, 6. I think that's what I want. I think. Let's find out. So let's just do torch h stack, y indices, x indices. And we'll call these indices. Why is this? Oh, because this guy has to be in like 2 or something. Print indices.shape. Seven, 2, 2, 5, 15. Okay. But then we want to keep a new dimension. Maybe? I feel like I'm missing something. Stack. Do I just want like a normal stack? No. But can I maybe just like reshape these guys now to n by self.sample -1 self.sample height self.sample width? Maybe is what I want. -196 is not valid for the input of that shape. Okay, so I've done something wrong. I've done something wrong. Let's think. When we saw before, it was 15. What we had before was n height plus width. Which I thought seemed reasonable, actually. Seems reasonable. So how do I get from here? So I need to get from n height and width. I need to use those indexes to get into something that's n by height by width. And I know that must be possible. I'm just missing it. I'm missing it. So for the image, I guess what happens if I just do this instead? N by y indices, x indices. So first I have an image and I sample from height a bunch of times. And then I sample from width a bunch of times. That looks like it might be it. We just gotta remove that fucking bullshit H stack that we don't need anymore. I think that might be it. It does say out of memory. Tried to allocate 149 gigs. Which doesn't sound right at all. Let's just do the Y indices and see what that gives us. This is giving me 725 by 9 by 512. I see. So what are we doing? I'm just trying to like fucking extract samples efficiently. So I have this like image, I'm trying to break it up into like samples that are defined by these like things that I've pulled out of the database. So the database I've pulled out like 00, 01, 02, and I'm just trying to like pull out the like equivalent sections of the image, and it's like I'm struggling to get there. Struggling to get there. So here I have indexes in Y, indexes in X for each sample. I just can't, I'm missing, how do I pull them out in a way that's like efficient? Because like these can't be broadcast together. That makes sense. They can't be. Let's like read the torch indexing rules again. So I'm trying to do like a 2-dimensional get. And what are the rules? Indexing a tensor works very similar to the Python API. Oh, I don't care about the C++ API. I just want the Python API. Indexing tensors. No, I want like their docs though. Torch index broadcasting. None of these look like what I want. None of them look like what I want. All right, we'll just look at slicing and striding. Okay, let's just read this and see if we find what we're looking for. Single element indexing for a 1D tensor works like expected. Yep. Okay, so nothing crazy here. Here he's doing ranges for 1 dimension, which means take every second. Oh, I didn't know you could do this. Take every second item from 1 to 10. That's pretty cool. Another special syntax is the n, meaning the size of the specified dimension. Okay. What about 2Ds? Adding a new dimension. Here we go. Dealing with variable number of indices. Sometimes we don't know how many dimensions the tensor have, but we do want to deal with the last 2 available dimensions. Okay, that's fine. I'm not worried about that. Vector indexing is also supported, but care must be taken regarding performance, as it must specify performance as slice-based indexing. Oh, that's interesting. So I kind of do want to use slice-based indexing if possible. Am I like... but you can't really store the slices, which is a little annoying, I guess. So here you say true, false, false, true, false, true, false, false, true. Okay. So these should just be indexing each of the dimensions. Okay. So this doesn't tell me anything. This doesn't tell me shit. I guess the problem is that I'm not trying to index contiguously, which makes this a little confusing. So image y indices, I think this just makes sense. This gives me, can I do like image.view y indices to avoid some of the like cost of because they're saying I run out of memory, but I shouldn't run out of memory because I shouldn't ever have to like allocate any memory at all, actually. All of these should be like views into the same thing. So they don't like view this way. Tuples of int size, I see. Torch. So when I do this, and I just index based off the y indexes that I have, I get 7,225 samples of 9 height things that I then need to pull out x width things from. So I don't really understand why I'm doing like this. Oh, maybe I need 2 colons. Seven two two five by 9 by 7225 by 6. I see, maybe. No, I don't see. Oh, it's because for each row, I'm not doing the same thing. Fuck me. Okay. Hear me out. I know what we can do. We can simplify this whole problem by stopping thinking about it in 2D. We have an image, which is height by width, but we can just convert this into something that's height times width. And then our indexing, I can understand it. I can understand indexing into one-dimensional thing, and we can just convert it back at the end. So our x indexes for each sample are going to be added to the y indexes for each sample. That makes sense to me. So we can say that our y indexes are essentially going to be y indices from the database times sample height, and the x indices are just going to be like the same x indices. And then we can say flat indices is going to be the y indices plus x indices. Yes. There we go. So then we can say indices is equal to y indices times sample height plus, no, times sample width. Because we're going by, we're skipping rows. Yes. And then we have image. No, not, fuck. This is wrong, because my y indices is height 9, x indices is height, is width x. So we need to go from, y, x, 720, like n, y, and n, x, to n, y times x. So for each y, I'm doing each x. We're close. We're very close. I think I can figure it out. We can figure it out. Which means first we want n, y, x, and then we can figure it out from there. Oh god, it's so close. We're so close. My poor head. I can't think about it well enough. What are your PC specs? The stream is flawless. Pretty good. CPU info. Really? LS CPU, maybe? There we go. I have a i7 9700K. Feels like maybe a little old now. What is that? What year is that? 9700. Okay. What year is that? 2021. So a couple year old CPU. And then my GPU is a 6700 XT, so a couple year old GPU as well. AMD. Come on, Google. This is... Has there been one generation since then? 0? I actually don't remember. It's been a minute since I've been looked into this stuff. Anyways, those are the specs. And then like 16 gigs of RAM. But I need to get more because I keep running out. It pisses me off. AMD GPU working well for you? So we were struggling a little bit with some inconsistency in GPU training. But overall, it's been surprisingly good, given that like PyTorch has just only recently added like support for AMD GPUs with like a CUDA compatibility layer. I get some like GPU crashes occasionally if I'm like in Blender and doing, like ray tracing. It's like decent, but like occasional crashes. I don't know if that's like better or worse than NVIDIA. The gaming on Linux is like shockingly good, right? Like, I'm using like open source drivers and playing Windows games through Steam, and it works like arguably sometimes better than on Windows. The only issue, yeah, overall pretty good. I would say that like I like the idea of using open source drivers like a lot. Like, so that sells me pretty hard on it. Yeah, I don't mind them. I don't problems seem fine. Seems fine. The card is like horsepower wise, it's pretty fucking good bang for buck. You miss out on like the ray tracing stuff that the like equivalent NVIDIA series gets you, I think, if I remember correctly. But overall, pretty sick. Assuming you're only talking about GPUs, technically we have things that are more powerful than our most powerful GPU. Yeah, that's fair. That's fair. My knowledge on the topic is limited, we should say. Okay, so what was I doing here? For each Y, I for each Y, I have an X. Sure. So here, let's just say that we want to get like n by Y by X. What do we do there? We have the X indices and the Y indices, and we say like, the stack seemed reasonable. Was that what we did before? Y indices, X indices. Let's just print out what that is. X indices. Oh right, this was in this. So this was 725 by 15, which isn't what we wanted. I feel like I'm like losing my mind. Torch for each Y and X. Or something. It's not giving me what I want. Not giving me what I want. I just feel like I'm there, and I'm just like, I'm missing some obvious thing. And it hurts so much. This feels like a common operation. Torch NY and X. Somebody must have looked this up before, right? Like, is this gonna give me anything? No, obviously not. Obviously not, because that's not how you search these fucking things. Torch operations. Oh, yeah, I'm a fucking idiot. This is broadcasting. No, I'm just a fucking idiot. This is, okay. So we have n by y, and we have n by x, and we want n by y by x, so we just do this. We do n by y by 1, n by 1 by x, and we add those together. Yeah, okay. Jesus. Okay, so x indices is equal to reshape is equal to x indices. Dude, I'm so mad. I feel like, and then this fixes the broadcasting problem. We can just use these directly. Oh, I'm so mad. I'm so mad. So this is, we're just gonna reshape this into x indices shape 0, 1, x indices dot shape 1. Or do the same for y, but on the other dimension. So y indices shape 0, y indices shape 1, 1. Oh, I'm so mad. I'm so mad. This took so fucking long for such a simple concept. So now I have these, and I think, just be able to index the image with those directly. I should be able to say image, y indices, x indices, and I bet you that fucking works. Print samples shape. I'm gonna be so mad when this works. Ooh. It's not. Which is interesting. How is this? Oh, because I've typed X here. These should be Y and Y. Hello, what are you up to? I was trying to basically okay, stream started with us pulling out a bunch of like labeling and sampling code for our AI into like some cache database. We reload back from the database and we're like, holy shit, it's just as slow to read from the database as it is to like extract the samples. And then we're looking at the sample generation code and we're going like, oh, that's like more efficient because we weren't doing like looping in Python. So we're doing some like PyTorch bullshit to try to get what we're looking for. And it looks like here we ended up with what we wanted. 700, 2,225 samples of 9x6. Fuck yes. Okay. All of that was a massive pain just to basically say that we want to pull out our samples without looping in Python. Easy. So this is now data. And we can now say, we can log time, data extraction, which is basically this. And this should be cheap now, I think. Before, well, we'll see. And let's get rid of these like prints. I hope it's absolutely faster. I wouldn't be shocked if it's not, but we will see. Data extraction, type annotations. Oh, because I need width here. Okay, data extraction, 25 milliseconds. That seems a lot better. But we'll see. So then we need to do the same thing where we then iterate the samples again, pull out the labels. There's probably a way to do this faster, but that's fine for now. Label extraction is this. And in here, we no longer do this or this or this. We just say the label is equal to the row. We do still need to iterate. Okay, so we'll do X, Y labels here. Okay, sure. And I guess we need a label for each data, so we can say that our labels equal to torch.tensor, or zeros of data shape 0, with a type of torch int64. Yep. And now, just for each of these, we basically just say that we enumerate the rows of the labels we get back from the database. And we just say labels I is equal to row 0. And I bet you that saves a fuck ton of time. So now the only problem is that our data is one-dimensional, but we might be able to live with that for now. Maybe. Maybe. Okay. We'll actually can just delete this as well. If this is fast, then we have the right answer. Like, it's good enough. No column labels, so it's not labels, it's label. No such column label? Oh, what is it called then? Generate dataset cache. It's label ID, of course. Of course. Labels I equals row 0, so he doesn't like that for some reason. Because this is the wrong thing here. Didn't I say labels is equal to torch zeros with the shape of data shape 0, data type is equal to torch int64. I must have lost this. And now it should be quick. Fuck. Oh, that's okay. So loading labels from the database took 65 milliseconds. Label extraction 30, data extraction 28. But I wonder if we can maybe that's a lot faster than it was before. I think we were at 150 milliseconds or something earlier. So we shaved a bunch off. But I think that we could probably do faster with let's see, log time iterate and log time data extract. Then down here we can say label iterate and label extract. Oh, and I'm being stupid here again. We don't have to do this. We can just say that the labels is equal to torch tensor rows, I think. D type is equal to torch int64, and that'll probably be faster and probably will work. Labels, label iterate, 10 milliseconds, or 0.5 now. And what is the shape of these things that we're getting out now? Just make sure everything's right. Print labels shape and print data shape. Okay, yeah. Okay, so that seems reasonable. Loading labels from database took 50 milliseconds versus when we do it without the caching. So this is the cached version, and we have the uncached version, which takes in the glyph cache here. So this went from 170 milliseconds down to 50, which is pretty fine, I think. And this is on CUDA, so let's check on CPU because we're taking like some like GPU CPU transfer costs that I don't want to. I want to make sure that we're generating the labels on the CPU is slow as fuck. But what if we load them on the CPU instead? Was this? Oh yeah, we're down to like 30 milliseconds. Where I actually don't know where most of this is coming from, which is interesting. But that's like a lot better. So there we go. I think I'm happy to call it there. There's a little bit of cleanup here to do. But I think overall, we're probably in a state where it's good enough. I'll probably do a little bit of cleanup off stream just to make sure that we get like the 2D-ness back from the end. But we're at 2 hours and 20 minutes and my head hurts and I want to break. I want to eat dinner and stuff. So thanks for watching, guys. I hope that it wasn't too boring just watching me struggle with indexing for too long. Yeah, if you like what you saw, I stream most days at around 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you miss a stream or you want to watch on YouTube or whatever, there's a YouTube link in the Twitch description. There's also a GitHub link there where the project will eventually be, and once this like is a little cleaned up, we have a little bit of work in progress cleanup to do before it gets pushed, but we'll be there soon. And if you're watching on YouTube and you want to come by, swing by on Twitch, say hi. There's a Twitch link in the YouTube description. Thanks for watching, guys. Catch you on the next one. Bye!